Donnay. I'm happy to open the last session for today. So it will be a session on isogenies. We will have 3 talks. The first one is about some fisherman problem. The talk is entitled Scallop, Scaling the Sea Fish. It's work by Luca De Feo, Taco Boris Fuoza, Peter Kutas, Antonin Leroux, Simon-Philippe Mertz, Lorenz Pani, and Benjamin Wesolowski, and Simon-Philippe is here.
Yes. Thanks a lot, Serge, for the introduction. Thank you, everyone, for attending the Isogenies session. I'm going to talk about our recent work, Scallop, Scaling the Sea Fish. This is a talk about cryptographic group action. Can you actually hear me? All right, yeah. This is a talk about cryptographic group actions. What is a group action? It's a function on a set where G is a group which acts on the set, and certain axioms are satisfied, namely that the identity element of the group acts trivially, and that if you act with a product on the group, it is the same as if you act consecutively with the factors of this product. Now, it's quite easy to see how to get a Diffie-Hellman style key exchange from a group action. If it's a commutative group that acts, you just fix a set element in the beginning, and then you have Alice and Bob both take a secret group element. They just act on this fixed starting element, and then exchange the resulting set elements, act again. As long as your group is commutative, they should arrive at the same set element in the end. And well, this can be used as your shared secret. Now, the problem that resembles the discrete logarithm problem in this context is called usually the vectorization problem. So if you're given 2 set elements, you want to find the group element that maps one to the other. And the parallelization problem is the one that resembles the computational Diffie-Hellman problem. This is quite a powerful framework. So if these problems are hard, even for a quantum computer, then this gives rise to a post-quantum secure key exchange. Probably the most prominent one is the Seaside key exchange, which is also like a non-interactive key exchange, very powerful tool to build other post-quantum constructions. And this talk is going to introduce yet another post-quantum group action that gives you even more properties. But what could you actually ask for more in the than Seaside? I mean, it's a very cool group action. You can build a lot with it. Well, for starters, Seaside is not an effective group action. What does that mean? You cannot actually evaluate it on all the group elements of your acting group. The truth is, Seaside, you can only evaluate it on certain fixed elements of your acting group, and this is for many constructions not a problem. Namely, you just restrict yourself to a list of elements, L1 to Ln, that span your acting group, and for which you can efficiently evaluate the group action. And then in practice, you just evaluate on product of these elements just by consecutively evaluating the group action. This is called the restricted effective group action, which is, as many of you will know, quite powerful. But there's some constructions where you would like to evaluate your group action on all the elements, and where you want to have a unique representation of every group element, for example. And for example, this is very useful to build Fiat-Shamir style efficient signatures. But Seaside doesn't give you that. So is there a way to transform a restricted effective group action into a effective group action? Yes, there is a general strategy. You can pre-compute the group structure of the acting group. So that means you pre-compute, for example, the cardinality of the group, and you pre-compute something that's called the lattice of relations. So if you have your generators from the previous slide, these L1 to Ln that span the entire group, you look for vectors in the exponents such that L1 to the Li to the EI, the products of those act trivially. So the exponents give you like a vector. Well, each one of these relations gives you a vector. If you consider all of them, that's a lattice, and this lattice is called the lattice of relations. If you compute the reduced basis of such a lattice that allows you to solve CVP instances efficiently, then this can help you to evaluate the group action everywhere, namely assume you have, for example, L1 to a very large power E. And in fact, the groups we're interested in are usually cyclic or nearly cyclic. So you can assume that if you can solve this problem, you can kind of evaluate the group action everywhere. Now, if you just want to straightforward with your restricted group action evaluate this, is not going to work, because for a large exponent, if you have to do it consecutively, it's just going to take too long. But what you can do is you just solve the approximate CVP problem in your lattice of relations. So you look for a lattice vector that is close to E followed by zeros in this case. So that gives you a decomposition or a product, Li to the EI, that acts in the same way on your set, such that the exponents are small. And well, now you can just use your restricted group action to evaluate it. The caveat, of course, with this idea is that depending on the group G, you may not be able to actually pre-compute its group structure. And in fact, for the groups that we have in Seaside, for example, the groups are notoriously known to be very hard to compute. However, this strategy was used by Bullens, Kleinjung, and Vercauteren in 2019 to build efficient isogeny-based signatures. There, they just took the Seaside 512 action, that is the smallest Seaside parameter set group action, pre-computed the lattice of relations with an index calculus approach, and then basically did the strategy from the previous slide. Now, the group action of Seaside is a class group action. So these class groups are well, hard to compute, and to compute the structure of this group, they did a world record class group computation. So this was the biggest class group ever computed to just get the smallest parameter set of Seaside into this effective group action framework. Unfortunately, it doesn't scale very well. So computing the structure of larger Seaside parameter sets is firmly out of reach with the currently known algorithms and computational resources. So this was the motivation for our work. Can we build a different group action from Isogenies in our case that solves this scaling issue? Can we somehow build effective group actions for larger parameter sets? And that scale at least to some extent. So to answer these questions, let's look a little bit at what the Seaside group action actually is. So for group actions on isogeny, you have an imaginary quadratic order. You can think of it as like some z squared of minus p for prime p. And then you consider as your set that you act on certain elliptic curves. These elliptic curves have endomorphism rings. That is the isogenies that you have from a curve to itself, and they have a certain structure. They are orders in a quaternion algebra, but each of them also has many embeddings of different quadratic orders into them. So it turns out that those elliptic curves that have an embedding of some fixed imaginary quadratic order in them, you can act upon by invertible ideals of this imaginary quadratic order. Principal ideals act trivially. So this gives rise to a well-defined group action of the class group. The class group is just the set of all invertible ideals of your imaginary quadratic order divided out by the principal ideals on the set. And now Seaside is the special case where you take the imaginary quadratic order z squared of minus p, and you consider curves that are defined over fp, the finite field over fp. And square root of minus p is under this embedding. This embedding is called the orientation, is mapped to the Frobenius endomorphism, which is well defined over curves defined over the base. Now, this raises the question: if we cannot compute the class group for this order a class, the structure of this class group for larger parameter sets, can we maybe do it for different imaginary quadratic orders? But if we do so, can we then still evaluate the group action? Like, we know it exists, but can we compute with it? How do you represent stuff? This is one question we answer in our paper for one family of group actions. But why would we want to do that? Why do we want to use a different quadratic order? The reason is that for certain quadratic orders, you can compute a class group of it more easily. If you have a imaginary quadratic order O of the form Z plus a conductor, that's called the conductor F, times imaginary quadratic order of which you know the class group or the class number, like the cardinality of your class group, then you can compute the class number just from the factorization of F. So that's a simple formula. You don't have to do some huge computation for that. So our strategy was we just take a class group that has a trivial, that acts trivially, so class number 1. And then we generate certain candidates or generators of a larger class group, or larger imaginary quadratic order, sorry, and compute the conductor. And if it's prime, well, then we know it's factorization. We can easily compute the class structure, well, not the class structure, but the class number, sorry. And we just sieve over these candidates until we find one class group that has reasonably smooth class number. So the cardinality is divisible by many small factors. Now, this is where our approach is also not super scalable, right? You still need to sieve through many candidates until you find a reasonably smooth number. If you just model this as the class number as being like a random number of a certain size. But if you have found one that is reasonably smooth, then we can compute the lattice of relations just by solving instances of the discrete logarithm problem in your class group, because, well, if it's reasonably smooth, you can solve discrete log problems. Then the rest is similar as was done previously in CFISH, namely, you just compute a reduced basis. This is also fine in our case because the dimensions we deal with, this is not going to be the bottleneck of the computation. And finally, we need to instantiate the group action with a starting curve. You need to find something to start acting on. This is not as straightforward as it is in C side, where you just take some curve defined over FP. But instead, we give a solution for this in our paper. And this is also efficient. Now, to actually compute the online phase, I said earlier, we generate the imaginary quadratic order to have a smooth generator. This smooth generator under the embedding into the endomorphism ring corresponds to an endomorphism of smooth degree. And these endomorphisms you can represent. You can write down a representation of it in terms of its kernel. And this endomorphism plays the same role that the Frobenius endomorphism plays in C-side. Namely, it stabilizes the kernel of the isogenies used to compute the group action. Now, on the right side, you see the isogeny graph involved. So all the curves on the outside are the ones that essentially you walk on in our group action. And they are all connected to one group with a trivial group action in the middle. And lines represent a large degree isogeny of degree F. Now, you can evaluate this group action similar to C-side by computing certain isogenies. That's maps between elliptic curves for this talk. The drawback here is that you have to transport your orientation, so this endomorphism along the curves. So there's some additional computation you have to do compared to C-side, where you have this as an implicit feature already available. And that's also why our group action is a bit slower. So let's just look at a brief comparison of CFISH and Scallop, our two isogeny-based effective group action. One has a fixed imaginary quadratic order, z squared of minus p, whereas in Scallop, we can instantiate all sorts of imaginary quadratic orders of this form z plus some prime times a like in our case, it's the Gaussian integers, the O0. While in CFISH, you have to do this very expensive class group action, which only allows you to compute the class group for the smallest parameter sets, and afterwards is infeasible. In Scallop, you get the class number, so the cardinality of the group for free. But you then have to do some sieving until this class number is smooth enough to compute this lattice of relations. Asymptotically, both of these steps are unfortunately actually have the same complexity. But in practice, the constant is much slower. So with even moderate resources, we managed to instantiate larger security levels with Scallop. The evaluation in CFISH is with this implicit orientation by the Frobenius endomorphism and is quite efficient. Unfortunately, our group action is less efficient because you have to compute this explicit orientation along the evaluation. We implemented our group action in C++, and it's available under this link. More precisely, we gave a concrete instantiation for Scallop that matches the security levels of C-site 512 and C-site 1024. Just a reminder, C-site 1024 would be absolutely infeasible with the CFISH type of computation. The public keys of our group action are roughly 1600 bits for the smaller parameter sets and 2300 bits for the larger one. That's still quite compact. It's larger than the C-side ones, but that's not the main problem. What's a bit more annoying is that the evaluation of the group action for the small parameter sets takes 35 seconds, and for the larger ones, 12.5 minutes for our parameter sets. And to, for example, build signatures from this, you would need dozens of these group action evaluations. So in summary, this implementation shows more the feasibility of our group action than, well, than its practicality. So in summary, we provide a framework to evaluate new group actions on oriented elliptic curves via isogenies. We give very concrete instantiation for class group actions using this imaginary quadratic orders of large prime conductor in a imaginary quadratic field of small discriminant. This is what we call Scallop. And this instantiates effective group actions for larger security levels that were previously out of reach. And allows you to build schemes where you have to uniquely represent elements and efficiently act by arbitrary group elements. Which gets us to the question. So the obvious ones is, how can we make this group action more practical, as in faster? And Scallop still has a scaling issue. We can do larger security levels, but they clock out eventually. Maybe there's a way to resolve that. Thank you for your attention. You will find a lot more details in the paper, and I'm happy to take questions.
Thanks for the interesting talk. I wonder the smoothness of the class group order, does it have any implications for the hardness of the discrete log problem or whatever the analog is? I think you call it vectorization problem.
For the class group action, we don't think so, no. Of course, it immediately influences how hard it is to compute the lattice of relations, right? The more smooth it is, the more easy it is to compute the lattice. But yeah, no, we don't think that it has security implications on the actual class group action.
Thanks.
Any other question?
Thank you for the nice talk. I seem to recall that C-side has this gap structure where you can, like, you have the underlying assumption gap CDH in pre-quantum cryptography, which is notoriously hard to find in post-quantum cryptography. Do you know if Scallop also has this? I think C-side was the only one previously known to have this gap structure.
What do you mean by the gap structure?
So with access to a decisional oracle, the computational problem should still be hard.
Yes, I think so, yeah.
Okay.
I mean, it's pretty much the same thing. Well, I think it's a very similar problem. So if you abstract away a lot of the structure, you get the same like general problem.
That makes sense.
Yeah.
Thank you.
Since there was another question in the back. Yes.
Oh, just a question that you were mentioning that you take the maximal order to have a class number 1 to sieve, right? So
Yeah.
why is it that?
You could also use another small one, or one that is known. We just we started working with Gaussian integers, and they on one curve you have like a trivial class group action there. I'm not sure you gain anything by taking a larger one. That's maybe interesting. I don't know. I don't think so.
Well, because there's only finitely many, right, with class number 1. So at some point you want to have a bit more.
No, but this is just your like if you look at the isogeny graph that I had here. So the one that has action of class number 1 is the one middle curve. And then basically the curves that are actually where you compute the group action are the ones on the outside circle. So ones that are connected by a large degree isogeny. And if the degree is large enough, you can basically reach many, many curves. And it depends on the conductor which curves you actually reach to compute your class group action on. So I don't think it really matters which curve you have in the middle. Like think of SIDH, you have like a starting curve in the beginning with a lot of structure, but then you walk away into all sorts of directions until you reach curves far away. Just that in our case, it's not a smooth degree isogeny, but a large prime. Yeah, I don't know whether this answers your question.
Yeah, no, it was just to find this order from the maximal order, that you started from a maximal order of class number 1.
Yes.
So I was wondering what's the technical, but anyways, if
it just has to exist. So
okay,
if you have one, that's sufficient.
Yeah. Okay, fine.
Okay, if there is no other question, let's thank the speaker again. So next we have a round optimal oblivious transfer and MPC from computational seaside by Sai Krishna Badrinarayanan, Daniel Masni, Pratya Mukherjee, Sikar Patranabis, Srinivasan Raghuranam, and Pratik Sarkar. Patrick Sarkar is here. Sorry for mispronouncing.
Hi, my name is Pratik. Today I'm going to talk about round optimal oblivious transfer and MPC from computational seaside. So this is a joint work with Sai Krishna, Badrinarayanan, Daniel Masni, Pratya Mukherjee, Shikhar Patnavis, and Srinivasan Raghuraman. So this work was done when all of us were at Visa Research, and now we are in different places. Only Srini is left in Visa. So let me first introduce what is MPC and OT, and then I'll go into the constructions. So I will talk about secure two-party computation. So there's two parties who have their private inputs X and Y. So they want to compute a function F on their private inputs. To do that, they run a protocol over here, and it's satisfied that the protocol output should be same as function output. And security says that the protocol should not leak anything about X and Y beyond the output. Now, a more specific two-party protocol is OT. So this OT primitive, there's a sender who has input messages M0, M1, and there's a receiver, she has a choice bit B. And now the OT protocol outputs MB to the receiver. Security says that the sender should not know B, and the receiver should not know what is M1 minus B. So this is a very simple primitive in the two-party setting. And this is a very interesting primitive because we know that round optimal OT gives you a round optimal MPC. So if you just build this OT primitive, you can go all the way up to MPC, which is a more generalized version of 2PC. So that's why we are going to focus on this round optimal OT in this talk. And in this talk, our focus is OT protocols in setup model and plane model, which are round optimal. So in the setup model, round optimality means 2 rounds, and in the plane model, it's 4 rounds. So that's why I'm saying round optimal. And then simulation security, as in you need indistinguishability based security, and also you will be able to extract a corrupt party's input. So that's what simulation security means. And finally, we will try to construct it from weak isogeny based assumptions. We will mainly construct it from computational seaside. And by applying the results of Ben-Muda et al. And Gerg et al., we will get MPC in setup model and plane model, satisfying the same properties which our OT protocol will satisfy. So now let me talk about our contributions and compare with state of the art. So in this work, in this talk, I'm going to focus on the seaside based protocols. I'm not going to talk about the SIDH based protocols. So in the seaside based protocols, there's 3 works which construct 2 round OT protocols in the setup model, mainly CRS and CRS plus random oracle model, and they satisfy UC security, but they rely on this decisional seaside assumption. So it's like a DDH variant of seaside. Then there's a recent work in Eurocrypt 21 by Lai et al. So they construct a 4 round protocol from reciprocal seaside. So this is a quantum equivalent to computational seaside. So they rely on CRS plus random oracle, but they are not round optimal because they require 4 rounds. And finally, there's a recent work by Orsini et al., which came out, I think, last month. So they rely on discrete log seaside, which is like the one-wayness of seaside. But they rely on knowledge of exponent assumption for the reduction, and they are round optimal, but they only obtain relaxed UC security because they get knowledge of exponent assumption. And finally, in this work, we build from computational seaside, which we wanted to go, and we get it in 2 rounds. So we actually get UC security. So this is a typo. This will be UC. And we get it in the CRS plus random oracle model. So our contributions is as follows. In the setup model, we obtain a 2 round UCOT in CRS plus random oracle from computational seaside. And we also obtain MPC by applying the results of BL18 and GS18. And now I'm going to talk about our results in the plane model. So in the plane model, there are 3 works which obtain OT protocols. So this work by Alamati et al., they are 2 rounds, they only obtain semantic security. They don't get simulation security. So they only have indistinguishability based security, where you get sender privacy and receiver privacy, but not extraction. So this is not full simulation. So that's why they can do with 2 rounds. And there are works, there's a work in TCC last year, where we construct a 4 round OT protocol in the plane model, and we get full simulation security. And as a result, we get MPC. And this is 4 round is round optimal in the plane model. And there's a work by Khurana et al., which by applying the result of ADMP20, you can get a 4 round plane model OT from decisional seaside. So as you can see, the literature is open for computational seaside. And in this work, we construct 4 round plane model OT and MPC from computational seaside. So this is our second contribution. So we get a 4 round OT protocol in plane model, which is simulation secure and from computational seaside. And we also get MPC by applying the result of BL18 and GS18. And finally, we also show an OT extension to show some efficient results. Our base OT requires 4 isogeny computations, and this protocol relies on reciprocal seaside, which is computational equivalent to computational seaside, quantum equivalent to computational seaside. So these are our main contributions. Now I'm gonna briefly talk about isogeny preliminaries. Simon has already introduced them in the previous talk. So this is a group action. A group action consists of a group and a set and a function star over here from the group and set to the set. And you need an identity element such that E star X is equal to X. And the group has to be abelian. And also G dot H star X should be G star H star X. And for any 2 set elements X and X prime, there exists a unique G in the group such that G star X is X prime. Next, There's something called effective group action, which Simon introduced in the last talk. That is, you can efficiently compute G star X for any G comma X in G cross X. And you have efficient EGA instantiations from C side with known group structure and C fish. And this is not broken due to the recent attacks on SIDH family of isogenies. There's also another abstraction called REGA, which is regular group action. And in our protocols do work in that regular group action framework. But in this talk, I'm not going to talk about it due to keep it simple. So these are the computational assumptions. So first is the discrete log C-side assumption, or the one-way EGA. So given a random group element G and a set element X, and given X comma G star X, it is computationally infeasible to compute G. So this is like one-wayness. And then you have the weak unpredictable EGA, which is like the computational C-side. So this is somewhat like the CDH variant of C-side. So here, given G and H and X comma G star X and H star X, you cannot compute, like an adversary, computationally bounded adversary cannot compute G dot H star X. So this is the computational C-side, or like the CDH variant of C-side. So our protocols are in this from this assumption, the second one. So now I'm going to talk about our OT protocol in the setup model. So we start off with the two-round semi-honest OT protocol. So here we assume that the sender and the receiver will follow the OT protocol, like when it's corrupted by an adversary. So in the CRS, you have three set elements X, X0, and X1. And now the receiver has choice bit B. It samples a random group element R, and it computes the first OT message as R star XB. It sends over this Z to sender. Now the sender computes two random pads by sampling K0, K1 from the group, and capital Y0 is K0 star X0, and capital Y1 is K1 star X1. And then the sender uses this K0 and K1, the randomness, to encrypt the messages M0 and M1. So the sender computes T0 and T1, which is hash of K0 star Z XOR M0, and T1 is hash of K1 star Z XOR M1. So this H is random oracle. And now the sender just sends Y0, Y1 and T0, T1 to the receiver. Now the receiver can compute MB, which is TB XOR hash of R star YB. So just given this randomness R and YB and TB, it can compute MB. So if you work out the algebra, then you can find out that MB is what it is. So this thing works out. And to argue that the receiver's choice bit B is hidden from a corrupt sender, we can show that this choice bit B is statistically hidden. So assume that B is equal to 1. That means Z is R star X1, and you can also write it as R prime star X0, where R prime is a function of the trapdoors of the CRS. So R prime can be written as R G1 G0 inverse. So you can express Z as both as the first message corresponding to bit 0 and bit 1. So that's why the choice bit is hidden. And now for sender privacy, we can show that if the receiver computes M1 minus B, then you can break the weak unpredictable EGA property. And for the reduction, we need to extract the R, this R, from a corrupt receiver. So this is semi-honest. And now to make it malicious, we can show that this protocol already satisfies security against a malicious sender. That is, you can extract M0 and M1 when the sender is malicious. But when the receiver is malicious, you cannot extract B and R, because recall that it was statistically hidden. So we need some additional primitives to get input extraction for a malicious receiver. So to do that, we introduce, get help from the literature. We use this primitive called non-interactive witnessing distribution proof of knowledge, or NIWI. So here there's a prover who has an NP statement X and witness W, and the verifier has the same NP statement X. And now the prover sends a proof called pi, which is there exists W such that X comma W is in the relation. And now the completeness says that verifier outputs 1 if X and W is in the relation. Soundness says that if X is not in the relation, then verifier outputs 0. And witness indistinguishability says that if pi 0 and pi 1 are computed using two different witnesses, then pi 0 and pi 1 are indistinguishable. And proof of knowledge says that witness can be extracted from an accepting proof. So we are going to use this primitive to get security against malicious receiver. And we also build this from WE-AGA in the CRS model. So this was our semi-honest protocol from the previous slides. And now we incorporate these NIVI protocols where the receiver uses a NIVI to prove that it knows R such that Z is R star X0 or Z is R star X1. And it sends the NIVI proof and the sender verifies the NIVI proof. Now, coming back to receiver privacy and sender privacy, the receiver privacy follows that choice bit B is statistically hidden and the pi is witness indistinguishable, that this does not leak about whether it's from X0 or X1. So this is witness indistinguishable. And for sender privacy, we again rely on this pi to extract the R, and this relies on pi sound and extractable, and then we reduce to our semi-honest sender privacy argument. And to do input extraction, you can extract from the NIVI, as I said before. And for sender input extraction, you use a CRS trapdoor to extract both M0 and M1. So this is our two-round maliciously secure OT protocol in the setup model. And yeah, and now I'm going to discuss our plain model OT protocol. So before doing that, I'm going to discuss the interactive variants of NIVI and zero knowledge. So in zero knowledge, you again have a prover who has input statement X and witness W, and the verifier has statement X. So it needs to satisfy completeness, soundness, zero knowledge. And proof of knowledge says that a witness W can be extracted from an accepting proof. And in addition, we need an additional property called delete input. That is only the last ZK protocol message depends on the prover's input statement X. So the first three protocol messages are independent of X. So this is an important property for our protocol. And we build this from WE-AGA as well. And next, another primitive is delete input WI, proof of knowledge. So this is same as the interactive zero knowledge, except this is WI, witness indistinguishable and not zero knowledge. And we need like 3 rounds. And this has to be also delayed input. That is only the last WI protocol message, depends on the statement. So this is delayed input WI proof of knowledge. So using these two primitives, we are going to build our plain model OT protocol. And we also build this protocol from WE-AGA in the paper. And so this is our 2-round semi-honest protocol, which is like the first protocol. So if you remember, the receiver had a choice bit B, it computed R and Z, and it sent it over. And this was the second OT message. And X0 and X1 was a CRS. So in this maliciously secure plain model OT, there's no CRS. So the sender is supposed to sample the CRS X0 and X1. So this is going to be OT2 message. And now I am going to briefly fill up the other 4 OT messages. So first I'm going to incorporate the WI primitive from the previous slide. So here using the interactive WI, the receiver is going to prove that it knows an R such that Z is R star X0 and Z is R star X1. So see that like the first 2 messages are just like the pre-processing or the here we need the delayed input property of WI because we don't rely on the statement over in this 2 first messages. So this is a 3-round delayed input WI which we are using here. And the verifier will now verify the WI in the 3rd round, and then it will compute the 4th round, which is like this second round of the semi-honest OT protocol, and send it over. And then to prove for like now to consider as malicious sender, we need to ensure that this X0 and X1 is correct, and we also need to extract the G0 and G1. So that's why we use the delayed input ZK protocol, the zero knowledge protocol, which was 4 rounds. So the first 3 rounds are like pre-processing, independent of the statement, and the final round ZK protocol message from the sender to the receiver is dependent on the statement, and it sends it over, and the receiver now verifies that. So after it verifies it, now it computes the message. So this is our 4-round plain model OT protocol, which is nothing but the 2-round semi-honest protocol plus a 3-round WI and a 4-round ZK. So that's how we can interpret our 4-round maliciously secure OT protocol in the plain model. And now to argue input privacy, we can see that B is statistically hidden, and the WI also hides what is B. And this ZK protocol has to be sound. And because if this X0 and X1 is badly computed, then you might be able to leak stuff. And finally, for sender privacy, if R computes M1 minus B, then we can break WA, and we also rely on WI sound and knowledge. And then for input extraction, we extract R from this PyWI, and we extract B accordingly by setting Z is R star XB. And finally, for input sender input extraction, you extract G0 and G1 from this PyZK, and then you compute M1 and M0 using the trapdoors G0 and G1. So this is our simulation security for the plain model OT. And finally, we build these primitives from WEAGA because there are known constructions of these primitives from weaker primitives like injective trapdoor one-way function and statistically hiding commitments 2-round. So you can build them from WEAGA. So to conclude, we constructed the first round optimal OT or MPC in the CRS plus random oracle model from computational C-side. We also built the first round optimal OT plus MPC in plain model from computational C-side. And we also have a OT extension based on reciprocal C-side, which is efficient. And to conclude with 2 open problems, can we build 2-round computational C-side based UCOT, which is like you need extraction for corrupt receiver and corrupt sender without relying on random oracle. So in our paper, we need the random oracle to extract the R for the reduction, but that is not really required for the simulation. So can you remove the random oracle and still get a UCOT? And finally, can you build a 2-round UCOT from computational C-side where you incur constant number of isogeny computations? So our protocol, recall that has a NUI inside it for the 2-round maliciously secure OT, UCOT, and that requires order of K isogeny computations. So that part is not constant isogeny. So can you do that from, can you do that from computational C-side without requiring security parameter number of isogenies? So thank you.
Thank you for the talk. My question is, what's the difference between UC security and simulation security? Which one is stronger?
UC security is definitely stronger.
What?
The UC security is definitely stronger, but in the plain model, you cannot get UC security. So simulation security is weaker, if that makes sense. So you need some kind of setup assumption to get UC security, but you cannot get that in the plain model. Okay. Because you have rewinding, so that is like UC incompatible. Maybe we can talk after this.
Any other question? Okay, so let's start your speaker again.
Okay.
And the final talk for today is entitled Generic Models for Group Actions by Julien Dumont, Dominique Hartmann, Eike Kils, Sabrina Kurzweiler, Jonas Lehmann, and Doreen Rippel. And Jonas is here whenever you're ready.
All right, can you hear me?
Yes.
Very good. All right, so this will be yet another talk on group actions. So there will be some overlap with the previous talk, so bear with me here. First, let's start the talk with some motivation. And for this, we take our favorite characters, Alice and Bob. They want to have a private communication over an insecure channel, like the internet. And therefore, they have to assume that there might be a malicious party, Eve, that eavesdrop on their messages and may read their secret. And of course, that's nothing that Alice and Bob want. And of course, we know how to solve this problem, right? We can just use encryption for this. And as long as Alice and Bob use a secure encryption scheme, Eve cannot learn their messages and in particular, not their secret. This has worked very well in the past, but since recently we know that there exists this notion of a quantum computer. And in particular, if Eve has access to such a quantum computer, then she can break almost all the public key cryptography we use today in the internet. And of course, then Alice and Bob's messages are not secure anymore. We know how to solve this problem again. We can use post-quantum secure cryptography for this. And there exist various approaches to this. And I guess the most prominent one is based on lattices. They have very, very favorable trade-offs. They are very flexible, and they have been recently standardized by the NIST. So we are pretty confident in their hardness and in their security. However, it's not completely ruled out that there's not some clever math that completely breaks lattices, right? Can never be sure about that. So what we like to do is we like to diversify. So we want to build protocols based on different assumptions such that if one of them gets broken, then the others might not. And one of these popular alternatives are cryptographic group actions. They come again in various shapes and forms, but the most popular ones are based on Isogenies. And this talk will be exactly about these cryptographic group actions. Now, let me quickly give you an introduction to group actions. You have seen this already, but bear with me here. So we first need a group for our group action, and also we need a set, which we call X, and we assume that this set is more or less structureless. And thirdly, we need a mapping, which is called star here in this case. And this mapping should fulfill some basic properties. Well, first of all, we take a group element and a set element X, and this mapping should map us to another set element G times X. And of course, the identity should act trivially on the set. So this is one property. And we want compatibility with the group operation. This means that G times H times X should be equal to G plus H times X. And as you might see, we use additive notation in this talk, so which is a bit unusual, but I hope you get along. There are more properties, but I will skip them for brevity here. And if you have now a group action, then you can define some pretty standard group action assumptions. The first one is discrete log. So given X and G times X, the task is to compute the G. The second one is CDH. So given X, G times X, and H times X, the task is to compute G plus H times X. And the third one is DDH. So given X, G times X, and H times X, and some set element Z, decide whether Z is G plus H times X. And again, these are pretty standard, right? We know of a quantum algorithm solving these, and in particular solving discrete log, which is the Cooper-Berg algorithm. It has sub-exponential time complexity, but this is thus far the best attack we know. So we are pretty confident in the hardness of these assumptions. However, you can also define some non-standard assumptions in the group action world. For example, a strong CDH. In strong CDH, you are given basically a CDH instance, so it's very similar to CDH. But you're given additionally access to these oracles, so these DDH oracles, where you might note that the first input is fixed. So it's not quite the gap problem we talked about before, but it's very similar. And this is not an esoteric assumption I came up with for this talk. This actually underlies the active security of the C-side key exchange in the quantum random oracle model, which we showed at last year's Asia Crypt. So it's a very, very important assumption. Now, secondly, you can also define strong square inverse CDH, which says that, well, given X and G times X, the task is to compute such a tuple here, where the first input Y can be chosen by the adversary, but then the adversary also has to compute 2G times Y and minus G times Y. And again, the adversary has access to these DDH oracles. And here again, this underlies the security of the group action-based password authenticated key exchange from Crypto 2022, and also in some mild variation underlies the security of the group action-based oblivious transfer from Eurocrypt 21. So here it's not really clear how hard these problems are, right? Because the intuition is that these DDH oracles shouldn't help you much when computing the CDH or when computing this tuple here, for example. But you could also imagine having quantum access to these oracles, right? And then it's really unclear how hard these problems really are. And whenever you're faced with such a situation, at least in the prime order group setting, what you would do is, well, if you cannot analyze them directly in the standard model, then you would resort back to idealized models where the analysis might be a bit easier. And then you get at least some confidence in their hardness. Of course, these models don't exist in the group action setting yet. And that's actually what this work is about. So we first define the generic group action model, which is based on the generic group model by Shoup. And here we can show that in some cases, this model is actually part of the generic group model by Shoup. And also we can show classical lower bounds for all these problems we saw before, like discrete log, CDH, and DDH. However, note that classical here really means non-quantum, because we can further show that quantum lower bounds are impossible, at least in this model. And secondly, we define the algebraic group action model, which again is based on the algebraic group model, where things are now much nicer in the quantum setting, because we can now give classical and quantum reductions between these non-standard assumptions and discrete log. All right, so let's first start with the generic group action model. And here the idea is that we give the adversary access to a generic group action that has no further structure. Now, how do we do this? Well, we take our group action and also define a labeling function sigma that maps from the set X to some bit strings. And this labeling function is drawn uniformly at random. These labels are also uniformly random. And now by concatenating these two, we get a generic group action on these labels. And the intuition now is that, well, the adversary only sees these labels, and for the adversary, it doesn't matter whether the group action is implemented via isogenies or codes, because he doesn't see the real set elements anymore. He just sees labels that are uniformly random. So he cannot come up with these labels himself, because the labeling function is part of the setup or of the model. So in particular, he cannot compute the group action himself anymore. And this is, of course, an issue. We can resolve this by giving the adversary oracle access to the group action. So this oracle OX computes the group action for him. And this works by, well, querying the oracle on a group element and a label for some set element X. And the oracle then returns a label for the set element G times X. And again, the idea is that the adversary cannot come up with this label himself. The only thing he can really do with these labels is check for equality. Now, of course, you could also extend this model with further oracles, but I will not do this for the sake of simplicity here. And lastly, I want to mention that this is an information theoretic model. So in particular, we give the adversary unlimited runtime and only bound the number of oracle queries, more or less. Right? So he can do whatever he wants, like inverting hash functions, solving LWE, but he cannot freely compute in the group action anymore, because that's what we bound. And this really models that the only source of hardness in this model comes from this group action. And in particular, this also means that we have an easy discrete log problem in the group G, because the adversary has free access to the group G, and he can compute discrete logs in as much time as he wants. And this also matches our intuition, because groups are inherently pre-quantum, right? And we don't want any hardness of the group action to come from a group, right? All right, so that's the model. What can we show in this model? Well, first of all, we can show that if the group order +1 is prime, then the generic group model by Shoup actually contains our generic group action model. And this condition here on the group order is a bit weird, but actually comes from the fact that in the generic group model, we have a multiplicative structure in the exponents, right? So if you exponentiate multiple times, then you get a multiplicative structure. And in our model, we have an additive group instead, which is for technical reasons. And this mismatch causes this weird condition here. Now, as an easy corollary, we now get that under this condition, discrete log is actually hard in our model. So for every adversary A in our generic group action model against discrete log, we can bound its success probability by Q squared over N, where Q is the number of oracle queries, that is the runtime of the adversary, and N is the group order. And this is exponential, so this in sum is negligible. Actually, by adapting the same proof techniques as in the GGM, we can also show that this holds unconditionally, even though the group order +1 is not prime. And then we essentially get the same bound. There's some constant factor here involved, but for simplicity, we leave it out here. Right. What about a quantum version of the generic group model then? Group action model, sorry. Well, in theory, this is easy to define, right? We just allow quantum access to the oracle. However, there exists an algorithm by Ettinger and Hoya, which is a generic quantum algorithm solving group action discrete log. It takes exponential time, which means it's not a real threat to group actions. However, it has only polynomial oracle complexity, meaning that it queries the oracle a polynomial amount of times and then has gathered enough information such that it can only solve a local optimization problem, so to speak. And well, this takes exponential time, but in our model, this is free computation, right? Because it doesn't take place anymore in the group action. And therefore, not even discrete log is hard in our model, which of course is kind of bad. Things are now much nicer in the algebraic setting. Here, we give the adversary concrete access to the group action, so no labeling function involved anymore. However, the adversary has to behave algebraically. And what that means is, well, when the adversary plays a game, for example, then the game might provide the adversary with some initial input in form of set elements here. And now, whenever the adversary comes up with a set element himself, and in this case, the set element y, it also has to provide an explanation for the set element, meaning a group element g and an index I such that g times xi equals y. And this, of course, also works quantumly. And lastly, we measure the runtime of the adversary in the number of unit operations, so classical runtime analysis. Now, what are the results in our model? I only show one in the interest of time. Remember the strong CDH assumption from before? We can actually show that this is as hard as discrete log, at least in the quantum algebraic group action model. So for every quantum adversary A, we can find two other adversaries B and C against discrete log, such that the success probability of A is essentially bounded by the success probability of B and C. And therefore, these problems are, they imply each other. Right. So this is the end of my talk. So in summary, we adapted the generic group model and the algebraic group model to the group action setting. Actually, in our paper, we include further algebraic properties of group actions, like twists in the isogeny case. And we proved information theoretic lower bounds on standard assumptions in the generic group action model. And further, we gave algebraic reductions between non-standard assumptions and group action discrete log. And with that, I'm happy to take your questions. Thank you.
Any question? Yes.
I think in one of your slides, you mentioned that the generic group action model is contained in the generic group model.
Right.
Could you define what exactly you mean by contained?
Well, you could think of it like this. So in the generic group model, you have the like multiplicative oracle where you can multiply two group elements. Right. But then again, you can also have like an exponentiation oracle more or less by double and or like square multiply, right? And this this exponentiation oracle is actually a group action, right? So in a certain sense, if you remove the standard group operation oracle and just include the exponentiation oracle in the GGM, then you get a group. Then you get basically our generic group action model. So that's what we mean.
Wouldn't, if you were to include just the exponentiation oracle in the GGM, wouldn't it still just be the GGM? Because you can just set the exponents to just 1 and 1 and have a standard operation.
Sorry, can you repeat the question?
If you were to have just the exponentiation oracle in the GGM, wouldn't it still just be the GGM?
No, because you cannot multiply two group elements anymore.
Oh, you're
add...
saying like separate exponentiation and separate
Right,
operation.
you have one oracle for adding inside the exponent
Right.
and one for multiplying in the exponent.
And
right?
you mentioned that this is based on Shoup's GGM.
Right.
And have you ever thought about like Morris and like how that would translate?
That's a good question. I think, yeah, I never thought about that actually.
Thank you.
Thank you.
Yes.
Hi, nice talk. So how do you model the twists? Because yeah.
The twists we model as an extra oracle here, right? Where the oracle gives back a label for minus g times x. Because twisting really means like taking the inverse of an element. And because we are we have an additive group here, we just take, it sends over a label for g times x and gets back a label for minus g times x.
But twist is like a public operation, right? So,
Sorry?
I mean, if you model it as an oracle, then you assume that the computing the twist is hard, or?
Yeah, but well,
Okay,
yeah,
maybe we can talk offline.
you could say that, yes, but this doesn't affect the reductions a lot.
Okay, thank you. Yeah.
Thank you for a very interesting talk. Can you give some intuition about how you prove the final theorem?
Which final theorem?
So on the next to final slide of the presentation or something like this.
Oh, you mean on this one?
Yes, exactly.
Yeah, I can. So because we are in the algebraic setting, the adversary always has to provide these explanations, right? And when he solves CDH, for example, then he has to give like a relative d log to either x, g times x, or h times x, and from that we can extract more or less the discrete log of one of the elements. And the other part of the bound here, this one is coming from simulating these oracles, right? We have to somehow simulate these oracles in quantum superposition, and for that we use the one-way to hiding lemma, and therefore we get the square root bound.
Thank you.
Right.
Okay. No more question. So let's thank the speaker again. So that's it for today. We have a dinner in 1 hour approximately.
Hi everybody, dinner at 6 in this area. Other than that, take time, enjoy Atlanta. We're done for today.